All right, I'm going to go through the practice problems on page 400 in your book, so do these along with me in your text so you have them for reference. So we started this in class, but the following reaction is exceptional in that single replacement species is both oxidized and reduced, which is interesting. So what mass of oxygen gas would be formed by the decomposition of 45.65 grams of KClO3? So it says what mass of oxygen. So we are looking for oxygen and we are looking for the mass of it. We are given an amount of KClO3 in grams. So I kind of like to map out my questions. This is something we did in honors chem as well. Now it does have a little side question. How should your answer compare to the mass of the reactant? When we think about this, we are decomposing or breaking down the KClO3 into two separate chemicals. So no matter what, our answer for our oxygen should be less than what we started with because our chemical itself, that mass is breaking down, so the piece for oxygen should be less than the piece we started with. So we need to change from grams of our KClO3 and we need to first change it to moles because we want to get to our other chemical. So we're going to go from grams to moles of that same chemical. That we're going to use our molar mass to do that. Then we want to go and change to moles of our oxygen, our other chemical, using our mole ratio. Then we want to use the molar mass of oxygen to find its number of grams. So each of those arrows is a separate step in our process here. So we're going to write down our given amount, 45.65 grams of KClO3. And first, we're going to do that first arrow. We are going to change it to moles. So we're going to change grams of KClO3 to moles of KClO3. Now, it'd be a good idea to have your periodic table handy so that you can look up the molar masses of your chemicals and add these up. So let me grab my calculator as well. So we've got a potassium with a mass of 39.1 plus chlorine, which is 35.45, plus 3 times oxygen, which is 16. So we get a mass of 122.55 grams per mole. That is our molar mass. That allows us to cancel out the grams of KClO3 and we're left with moles of KClO3. So our next step is to change our chemical. We want to get rid of KClO3. And in our reaction, in our question, it's asking about oxygen. So this is our opportunity to change chemicals once we're in moles. Now we're going to use our mole ratio, which is the coefficients on the balanced reaction. So our coefficient in front of oxygen is 3, and in front of potassium chlorate is 2. So it's a 3-to-2 ratio. Setting that up allows us to cancel moles of KClO3. We're done with that chemical now. And we can do our final step. We want our final answer to be in grams for oxygen. So we want to change our moles of oxygen to grams. So again, we always, as you notice, copy our unit from the top left to the bottom right. Every single time we're always copying that unit down. For this last step, again, it's a molar mass. The mass of oxygen is 16. We've got 2 of them, so 32 grams per mole. And then we do our math. We can also cancel out moles of oxygen. We're left with grams of oxygen, which is what we want. So 45.65 times 3 times 32 divided by 122.55 divided by 2. And that's exactly how I put it into my calculator. I get 17.88. And that's with 4 significant figures on our given. So 4 significant figures in our answer. Okay, so this process is a way of finding any information out about a chemical reaction based on what we are given. So we were given 45.65 grams of potassium chlorate, and we wanted to figure out how much oxygen can we produce from that. So we got 17.88 grams of oxygen. Again, it is less than what we started with, which makes sense because the rest of that mass, if 17.88 is our oxygen, then the rest of the 45.65 should be the KCl. It breaks down. So there's our first example. Let's do another one. All right, number 2, it says this unbalanced equation shows one possible set of products for the reaction of aluminum and nitric acid. So first thing we need is to balance it because we can't do a mole ratio with an unbalanced reaction. So let's take a look. Excuse me. So I can see on my right side that I've got 3 nitrates because that 3 outside the parentheses. So I need 3 nitrates on the left. I need 3 of these guys. So I'm going to put a 3 out front. I can see from there that gives me 3 hydrogens. Now that's going to be hard to balance with this H2. So I'm going to probably have to double things. So I'm going to go ahead and go back and I'm going to reset here and just go ahead and start by doubling this amount. So now I have 6 nitrates. So I'm going to put a 6 here. That gives me 6 hydrogens. So I need a 3 in front of my H2s. And then I've got 2 aluminum atoms. We can see once we're done balancing those coefficients, if we can't break those down and simplify those coefficients at all. So kind of makes things, it's a way of checking yourself, making sure you're good. So now we've got a balanced equation. We want to determine the mass of nitric acid. So here's our nitric acid. We want to know how many grams we have. How many grams are required to form 170 kilograms of hydrogen gas. So we are making, excuse me, 170 kilograms of hydrogen gas. So now, if we want to approach this, we can take a similar approach to our last problem. We would need to change these to grams first, and then we would be able to use our molar mass to change it to moles of hydrogen. We would then need to change to moles of our nitric acid, and then we could get to grams of nitric acid. So we're going to set that up. 170 kilograms of our hydrogen gas, and first we're just going to get that to grams. So there are, so in kilograms to grams, or kilograms are bigger, so in 1 kilogram there are 1,000 grams, and then that gets rid of kilograms. So grams of hydrogen, and we want to change it to moles of hydrogen. So in 1 mole, the mass of hydrogen is H2, so 2.02 is its molar mass. That allows us to get rid of grams of hydrogen. Our next arrow goes from moles of one chemical to moles of the other. So we are going to change chemicals, go from moles of hydrogen to moles of nitric acid, HNO3. We're going to use our coefficients, 6 moles of HNO3 for every 3 moles of hydrogen. Cross out our hydrogen, moles of hydrogen. And now last thing, we want to change from moles of nitric acid to grams of nitric acid. Oops, HNO3. So in 1 mole, we need the mass of that. So hydrogen is 1.01, nitrogen is 14.01, plus 3 oxygen, so 3 times 16, and that gives me 63.02 grams of nitric acid per mole. And that allows us to cancel the moles. So now we do our math. So I'm going to do 170 times 1,000 times 6 times 63.02 divided by 2.02 divided by 3. This is quite a large number because we did have to multiply by that 1,000. So I'm going to put it in scientific notation. We've got 2 significant figures in our given because that 0 doesn't count. So my answer would be 1.1 times 10 to the 7th. Again, make sure you're practicing this calculation in your calculator to make sure that you're getting them correct, that you're putting in your calculator correctly. That's a way of checking yourself. Excuse me. So if we react 170, or we make 170 kilograms of hydrogen gas, if we form that, we would need to react 1.1 times 10 to the 7th grams of nitric acid. So that is, let's see, 10 to the 7th would be 1,000 million, 1, 2, 3, 1, 2, 3. So about 10 million grams of nitric acid. That's a lot, or 11 million. It's a crazy amount. So that's what we would need to do for that. So these are the kinds of problems that we can answer with this. For instance, if I was in an industry and I needed to create hydrogen gas through reacting nitric acid, this is, I could find out how much hydrogen I can make or how much nitric acid I needed to use. So in our next one, we've got hydrogen gas can be used as a reducing agent in the production of pure boron from boron trichloride. So it's describing our reaction. How many moles of boron, so we are looking for moles of boron, would form from the reduction of 500 grams of boron trichloride with excess hydrogen. So hydrogen is in excess, which means we have way more than we need. We don't really need to deal with that. So this one's a little different. It's giving us grams of a chemical, so we need to change those to moles, and then it's only asking for moles of the other chemical. So we only need to do 2 conversions this time. So we're going to start with 500 grams of boron trichloride, and we're going to start by changing those grams into moles using our molar mass. So boron's mass is 10.81 plus 3 chlorines, so 3 times 35.45, and we get 117.16 grams per mole of BCl3. And that allows our grams to cancel. Now we want to change from moles of BCl3 to moles of just boron. We can see from our balanced reaction it's actually a 2-to-2 ratio, and that allows our moles of boron trichloride to cancel. So in terms of your math, it kind of simplifies things. The 2 over 2 could be 1 over 1. So we really just have 500 divided by 117.16. And we've got 4 sig figs here, so we have 4 in our answer. So 4.268 moles of boron would be our answer. So since it asks for moles of boron, that's where we're going to stop. Okay, so some questions don't have to go all the way to grams of the next chemical. All right, we've got one more to try out. So it says write the balanced equation. So I've written that for you guys. Again, most of the time on the AP tests, they're going to give you that. So we've got the reaction between sodium metal and water. So when that occurs, it does ask in the question how many moles of hydrogen gas are formed, so that gets kicked out. And sodium actually reacts with water to form a base, a strong base, sodium hydroxide. So it says how many moles of hydrogen gas, so we are looking for moles of H2, would form if 2 moles of sodium reacted with excess water. So we are reacting moles of sodium. So this is actually very straightforward. It's asking us to react 2 moles of sodium, which is given in as our coefficient there. So if 2 moles of sodium react, it would produce 1 mole of hydrogen gas. So we really don't even have to show math on that. We can just show that it's a ratio. That's fine. Now, there is a follow-up question. It says, what volume would this gas occupy at STP conditions? So we've got a mole of hydrogen gas. So let's think about this. 1 mole of gas at STP is equal to 22.4 liters of gas at STP. So we can use that to convert. And because we have 1 mole, and 1 mole is 22.4, we got 22.4 liters of hydrogen. So this question really didn't require a whole lot of math. It's just a little bit of thinking. Sometimes like with this type of thing, it'd be more of like a multiple choice question. So that gives you some examples of some problems. Now, to try out for your homework, again, here we go. The section review for 6.5 is all going to be due on Thursday. So I would really encourage you to get started on it. We're going to skip number 13. So completely skip that one, cross it out, but we will do all of the other ones. If you want to just focus in on doing some conversions with grams, like the grams of one chemical to grams of another, or between moles of chemicals, you could focus on numbers 1 and 2, 6 through 11, and 14 and 15. Do as many of those as you can, maybe. find out where you've got some questions. Maybe try even just this part 1 and 2 and then 6 through 11. That would give you a good chunk of practice and really break things up over the next couple of days. We will do some more examples tomorrow where we incorporate more of like molarity and volume and things like that as our other tools and see how this works and extend it. Okay, thanks guys.